Well, hello. Today we're going to be talking about some more probabilities, and specifically we're going to be talking about and or problems with our probabilities. So you'll see these with things like what's the probability of drawing a queen or a red card or something like that. So that's the kind of probabilities we're going to be looking at today. These are called compound probabilities. Okay, so it means that you're looking for more than one thing to happen, compound. Okay, so the word or in math means that at least one of these things is going to happen. Now, this is what we would call an inclusive or. See, we've talked about this, you would have discussed this earlier in the year when you're talking about sets and set notations. Or is the same thing as the union, if you remember that, dealing with this type of notation. Like A union B, that would be A or B. But usually in probabilities, we use the word or. This is called the inclusive or. So at least one of the things is going to happen. Okay, both of them could happen as well. All right, so to find the probability of A or B, you would add up the probability of A plus the probability of B, and then you have to subtract off the overlap. Now, we're not subtracting off the overlap because we're saying like, oh, it's not allowed to happen in both. It's A or B, and definitely not both. That's not what this is saying. What this is saying here is we're going to add up all of A, we're going to add up all of B, and then the reason we subtract the overlap is because they got double counted. If you remember back into our set theory and talking about Venn diagrams, A or B, we would add up all of the amount that's in A, that's all this amount, and we'd add up all the amount that's in B, that's all this amount, and this part right here in the middle, it got counted twice. So we subtract it off once so that we get an appropriate number. Okay? So that's the reason for the subtraction part of this. Now, two events are said to be mutually exclusive if it's impossible for both events to happen at the same time. Okay, and then we would say that P of A and B, the intersection, having both of them happen at once, that probability is 0. Okay, so that would be maybe like drawing, if we're talking about a deck of cards, drawing a 3 and a 5 on the same draw. Like that would be impossible. You can't draw a card that has both the number 3 and the number 5 on it. Okay, so anyways, if you have two events that are mutually exclusive, then probability of A or B just becomes probability of A plus probability of B. And the reason for that is because the overlap would be 0. Okay, let's get on to some of these cards. Hopefully you know what's all in a deck of cards. Again, we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Of course, the ones are aces. And then we have jacks, queens, and kings. We have those of hearts, diamonds, spades, and clubs. If you're not sure what's in a deck of cards, just do a quick Google search for deck of cards, and you'll see everything. All right, so determine the necessary probability. So the probability of a king, well, there are 4 kings in a deck of cards. Of course, this could be reduced down to 1/13. I almost always leave this as 4/52, though. The probability of a red card, well, half the cards are red, so you actually know it's going to be 1/2. But if half the cards are red, that means 26 out of the 52 cards are red. So 26 out of 52. Now, the probability of king and red, okay, that means red kings. Well, how many red kings are there? You have the king of hearts and the king of diamonds. So there's 2 of them that are both red and king. So when we plug them all into the formula, probability of A, or in other words, the probability of kings, plus the probability of red cards, minus the probability of red kings. And again, I just want to remind you, we're not subtracting off the red kings because we're saying, oh, they're not allowed. We're subtracting off the red kings because the red kings, the king of hearts and the king of diamonds, they got counted twice, right? King of hearts got counted here with the kings. And king of hearts got counted here with the red cards. King of diamonds got counted with the kings, and it got counted with the diamonds. So that's why we have to subtract them off, because they got double counted. Now we're just going to do 4 plus 26 is 30, minus 2 is 28 out of 52. Okay? All right, so then that, when we divide everything through by 4, that's going to get us 7/13. All right. Using a standard deck of cards, what's the probability of drawing a queen or a club? So we look at the queens, and we'll do 52. There are a total of 4 queens. We look at the clubs, and we would say there are 13 clubs, right? 1/4 of the deck. So there's 13 clubs, basically 1 through 10, and then jacks, queens, and kings. That's 13 of them. Queen and clubs, there's only one card that has a queen on it and is also a club. So when we plug these into our formula, we would have 4 50-seconds plus 13 50-seconds minus 1 50-second. That's 17 minus 1 is 16 50-seconds. And that's just fine for an answer. If you divide everything through by 4, you get 4/13 though. And that's also a nice answer. Okay. Also, you can see up here, the reason I leave all these out of 52 is because I know I'm going to be adding them up. I got to get common denominators. So it'd be silly to change this down to 1/13 and change this one down to 1/4 and then 1 52nd. I just leave them all as 50 seconds. It's just easier, a little quicker. We can reduce at the end. All right, so of our numbers, let's say we take the numbers 1 through 10, we write them on pieces of paper, and we drop them all into a hat. Determine the probability the piece of paper selected contains an even number or a number greater than 6. So what we're looking for is the probability of even, or, you could write or if you want, maybe I'll come back and do that in a minute, or greater than or equal to 6. Nope, just greater than 6, sorry. So this is what we're trying to find. Probability of even or greater than 6. So the probability of an even, let's see, we've got 1, 2, 3, 4, 5 of them. 5 numbers are even. And we're going to add to that the numbers that are greater than 6. So that's 7, 8, 9, 10. So there's 4 of them that are greater than 6. Then we have to subtract off the overlap. And you can look up here and see, you can see the ones that are blue, the ones that also have yellow behind them, and it's kind of this green, those are the ones that are double counted. Those are the ones that we have that we got counted twice. So this is 2/10. So I get 5/10 plus 4/10 minus 2/10 is 7/10. Okay? 7/10. Now, you could also just go through and identify all the ones that work. Like if you're looking for probability of even or greater than 6, just go through and highlight every one of them that works. Turns out there's 7 of them. Okay? All right. And problems, the probability of A and B. So this is where we're going to be multiplying them. We're going to take the probability of A times the probability of B. Okay, so we are always going to assume that event A happened already when we're figuring out B. Okay, don't really worry about that too much for the problems we're doing, but just sometimes a few people get caught up on this. Like, well, what if this happens? What if it doesn't happen? Well, if we want the probability of the A and B both happen, you're going to assume that A happens and then assume that B happens after that. Okay? All right, so what's the probability of drawing 2 aces in a row without replacement? Well, what we're going to be doing is the probability of an ace, and then we're going to take that times the probability of a second ace. And I'm going to write it like this. This isn't really the proper math notation because we actually have to use something called given, but we'll look at that in another lesson. It's conditional probability. But let's just think about it. How many aces are there? There's 4 out of 52. Now, what's the probability that we we do this, again, this is without replacement. We looked at that before. We've taken an ace, maybe an ace of hearts. We take that, we set it to the side. We're like, okay, let's take this and we'll set it over here to the side. And now how many aces are left? There are 3 aces left. And how many cards total are left? 51. Okay? So that gets us 4 out of 52 is the probability for the first ace. 3 out of 51 is the probability for the second ace. Okay? And then these do reduce down pretty nice, actually. And if you're going to do this by hand, 4/52 is just 1/13. And then this one's kind of weird, but 3 does go into 51 17 times. So these reduce down, and then you can multiply this 13 times 17 to get 221. Of course, you could multiply across the top here, but you're going to get some pretty ugly numbers that you then just have to reduce. I'm using a calculator on it. So we get that, and then you reduce it. But I could do this one without a calculator if you just do some reducing. These are both equivalent. So this is the likelihood of you drawing 2 aces in a row without replacement. Now there's something called independent and dependent events as well. Okay, when the occurrence of any 2 or more events in no way affects the probability of others, then the events are independent. Okay? Dependent events means that the probability changes each time. Now, if you think about what we just did with our aces, we did that without replacement. And did you notice that in the second time, I'm going to go back to that, the second, drawing the second ace was actually a lot different probability. Drawing a first ace is 1/13, and then when you leave it out of the deck, the probability of getting another ace, it actually changes. That means it's dependent probability. When you do things without replacement, they're dependent. When you do them with replacement, they're independent events. So that's just some terminology that you can work on there. All right, let's say we have a bag of marbles that contains 5 reds. There we go. So 5 reds, we've got 8 blues, and then we have 5 yellows, and we have 6 greens. I didn't have a yellow pen handy. Selecting 3 marbles without replacement, find the probability the first one is green, the second one is red, and the third one is blue. Now, something really important here is that we're doing this without replacement. That means that we're dealing with dependent probabilities. So, without replacement, probability of a green, and we're going to take that times the probability of a red, then we're going to take that times the probability of a blue. And this isn't, again, it's not the proper notation because it's actually the probability of a red given green. And then this last one is the probability of a blue given that red and green were already drawn. So, but this is a simple notation. Okay, I'm just saying that for those of you that have already done conditional. You're like, wait a minute. So, probability of a green. Well, there are 6 greens, and there are 24 total marbles. Okay, so 6/24. Now, since we're doing this without replacement, we reach in, we pull out a green marble, we look at it, we cast it aside, and we're going to reach back into the bag. Now, how many red marbles are there? There's 5. How many marbles total are there? 23. Not 24, because we took that green marble and we threw it away. So now there's only 23 red marbles left in the bag. Now we're going to reach we took the red one, we threw it away now. We're going to reach back in the bag. Okay, we've already taken out a red and a green. That means there's only 22 marbles left. And now let's look at the blue one. Okay, there are 8 blue marbles. Now, you could just multiply all these and then work on reducing. I'm actually going to do a little bit of reducing. I'll show you how I would reduce these. 6 and 24 reduce down to 1 and 4. I would probably take the 4 and the 8 and reduce that down to 2 and 1. Then I would probably take the 2 and the 22 and reduce that down like that. Now I have much smaller numbers. And I think this is it now. 1 times 5 times 1 is 5. And on bottom, I have 1 times 23 times 11. Okay, so 23 times 23 is 2. I don't know why I did it that way. That was weird. Should be, oh, no, I did it right. 23 times 11 ends up being, for some reason, thinking 23 squared. So 253 is what 23 times 11 is. So 253. So 5 out of 253 is the likelihood that this scenario plays out. That you reach in and you draw out 3 marbles, and this is how they come out. Green, then red, then blue. Okay? All right, let's look at just one more quick one, and then we'll be done. Why don't you go ahead and find the probability of drawing out 3 balls from here, and the first one is a football, and the second one is a tennis ball, and then the third one is a baseball. Okay, so the football, well, you can see that there's a total of 7. That means that's our bottom number. Okay, and again, I wanted to reiterate that we're doing this without replacement. That's the first thing to notice. So football would be 3/7. Then we'll say the second one is a tennis ball. Well, there's only one tennis ball in there. Remember, we're doing this without replacement. So there's only 6 balls left in the bin because we took one of the footballs and we threw it out. Now we reached in and there's only 6 balls left, and one of them is a tennis ball. We pull it out, and now we're looking for the third one to be a baseball. There's only one baseball, and there's 5 balls total. I can do some reducing. 3 and 6 reduce down, and that's going to make this go just a little bit cleaner to be 1/70th. Right? 7 times 2 times 5. That's going to be 70. So 1/70th is our probability. All right, guys, I hope this was helpful to you. Good luck, and I'll see you next time.